Imagine a world, not so long ago, where giants walked the earth, a world dramatically different from our own, yet intimately connected to our shared history. Picture vast, sun-drenched savannas stretching to the horizon, dotted with towering megashrubs and ancient trees. Envision chilly, windswept tundras, punctuated by groves of hardy evergreens, their branches laden with snow. This was the late Pleistocene epoch, a time of breathtaking biodiversity, a living tapestry woven with beasts of unimaginable scale and power. This wasn't some distant alien planet, but our planet, a vibrant, dynamic Earth teeming with creatures that would seem mythological to us today. They were the architects of their ecosystems, the titans of their terrains, shaping landscapes and driving evolutionary narratives for millions of years. Their very presence infused the world with a sense of raw, untamed majesty. But then something happened, something catastrophic, something that irrevocably altered the course of life on this planet, leaving behind a profound silence where once there had been roars, trumpets, and thunderous hooves. So when we talk about megafauna, what exactly are we talking about? The term itself, derived from Greek, literally means large animals. Scientifically, it generally refers to terrestrial animals with an adult body mass exceeding 44 kilograms, or roughly 100 pounds. But for most of us, when we hear megafauna, our minds conjure images of something far more impressive, far more awe-inspiring. We're talking about the true behemoths, the charismatic giants that dominated their landscapes. We're talking about the mighty woolly mammoth, Mammuthus primigenius, whose shaggy coat and enormous tusks allowed it to brave the harshest tundras. The fearsome saber-toothed cat, Smilodon fatalis, with its dagger-like canines, the apex predator of the Americas. The colossal giant ground sloth, Megatherium americanum, standing taller than an elephant on its hind legs, capable of ripping branches from trees. Imagine the bizarre armored tanks that were glyptodons, resembling Volkswagen Beetles with tails, or the magnificent Irish elk, Megaloceros giganteus, whose antlers spanned an astonishing 12 feet. Let's not forget the shaggy woolly rhinoceros and the formidable cave bear. These weren't isolated curiosities, they were integral components of a complex, interconnected web of life. And these giants weren't confined to a single continent, they were a global phenomenon. From the frozen steppes of Eurasia to the vast plains of North America, the dense forests of South America, and the ancient landscapes of Australia, megafauna thrived. Each continent boasted its own unique array of these magnificent beasts: diprotodons in Australia, toxodons in South America, cave lions across Eurasia. Their global distribution speaks to their evolutionary success, their adaptability, and their crucial role in shaping ecosystems worldwide. They were the gardeners of the planet, the architects of nutrient cycles, and the very embodiment of wildness. Now let's pinpoint the exact moment of this seismic shift. We're focusing on a specific pivotal juncture in Earth's history, approximately 11,700 years ago. This date is not arbitrary. It marks a profound environmental turning point. It's the geological boundary that signifies the official end of the Pleistocene epoch and the beginning of the Holocene epoch, the very geological period we live in today. More crucially, this date marks the final dramatic conclusion of an extraordinary climatic event known as the Younger Dryas. Imagine a world that had been slowly emerging from the depths of the last ice age, gradually warming, glaciers retreating. Then, suddenly around 12,900 years ago, the planet plunged back into an intense cold snap. For over 1,000 years, temperatures plummeted, ice sheets re-advanced, and arid conditions spread. It was a dramatic global blip in what was otherwise a warming trend, a final brutal gasp of the glacial world. And then, just as abruptly as it began, the Younger Dryas ended. Around 11,700 years ago, the planet experienced one of the most rapid and dramatic warming events in its recent history. Global temperatures soared, glaciers melted at an astonishing rate, sea levels rose, and climates stabilized into the warmer, wetter conditions that characterize our current Holocene. It was a time of immense environmental upheaval, a grand reset for global ecosystems. It's within this narrow, turbulent window of rapid change that our story unfolds. A story of loss on an unimaginable scale. It is within this crucible of environmental transformation that we encounter the staggering, heartbreaking statistic that lies at the heart of our mystery. 42% of the world's large mammal species simply vanished. Think about that for a moment. Not a small percentage, not a gradual decline over millennia, but nearly half of all megafauna genera across the globe disappearing within a relatively short geological timeframe. This wasn't just individual animals dying. This was entire lineages, millions of years of evolutionary history erased from the Earth's surface forever. To put this into perspective, imagine waking up tomorrow to a world where nearly half of all the large animals we know today Elephants, rhinos, giraffes, bears, big cats suddenly ceased to exist. The ecological reverberations would be catastrophic, the silence deafening. That's the scale of the loss we're talking about, a mass extinction event that fundamentally reshaped every continent. The impact wasn't uniform, however. Some regions, like North and South America, were hit particularly hard, losing a staggering 70-80% of their megafauna. Australia also suffered immense losses. Africa and parts of Eurasia surprisingly fared better, retaining a significant portion of their iconic large animals. This geographical disparity is a crucial clue in our investigation and a source of intense scientific debate. But regardless of regional differences, the global average of 42% represents an almost incomprehensible biological tragedy, a profound amputation of Earth's biodiversity. It was a silent disappearance, leaving behind a void that the world has never truly recovered from. So, we have the players, the magnificent megafauna. We have the stage, a planet undergoing dramatic climatic shifts at the end of the last ice age. And we have the shocking outcome, 42%, nearly half gone forever. But with this knowledge comes the most compelling and enduring question. Why? Why did this happen? What force or combination of forces could have led to such a widespread and synchronized disappearance of these powerful, adaptable creatures? This isn't a simple question with a straightforward answer. Unlike the famous dinosaur extinction event, which points to a single cataclysmic asteroid impact, this megafaunal collapse presents a far more complex and tantalizing mystery. There's no obvious culprit, no single smoking gun. Instead, the scientific community has grappled for decades with competing hypotheses, sifting through geological records, fossil evidence, and archaeological data, trying to piece together the fragmented story of this ancient tragedy. The debate largely coalesces around two primary suspects, two powerful forces that were undeniably at play during this critical period: rapid climate change and the burgeoning impact of humanity. Was it the dramatic warming and ecosystem restructuring that simply overwhelmed these specialized giants? Or was it the arrival and rapid expansion of a new, highly effective predator, Homo sapiens, that tipped the scales against populations already under stress? Or was it a more insidious combination, a perfect storm that these creatures, after millions of years of success, simply could not weather? This is the core mystery we aim to unravel. In the episodes to come, we will embark on a fascinating journey of scientific investigation. We'll delve deep into the competing theories, examining the intricate evidence that supports each one. We'll explore the sophisticated tools and techniques scientists use to reconstruct Earth's ancient environments and trace the movements of both animals and humans. We'll weigh the arguments, confront the challenges, and highlight the ongoing debates that continue to shape our understanding of this pivotal moment in Earth's history. By understanding why 42% of megafauna vanished 11,700 years ago, we not only gain profound insights into our planet's past, but also confront crucial lessons for our present and future. Lessons about climate, ecosystems, and humanity's enduring, often devastating impact on the natural world. Join us as we seek to solve the silent disappearance. Welcome to a journey back in time, to a world that was both familiar and startlingly alien, the late Pleistocene. This was an era teetering on the edge of profound change, a mere blink in geological time that witnessed the disappearance of an astonishing 42% of the world's largest animals, what we commonly call megafauna, around 11,700 years ago. Before we delve into the why, we must first understand the what and the where to truly appreciate the grandeur of the world these magnificent creatures once inhabited. So, let us set the stage, painting a vivid picture of the late Pleistocene world. Welcome to a journey back in time, to a world that was both familiar and startlingly alien, the late Pleistocene. This was an era teetering on the edge of profound change, a mere blink in geological time that witnessed the disappearance of an astonishing 42% of the world's largest animals, what we commonly call megafauna, around 11,700 years ago. Before we delve into the why, we must first understand the what and the where, to truly appreciate the grandeur of the world these magnificent creatures once inhabited. So let us set the stage, painting a vivid picture of the late Pleistocene world. The late Pleistocene world. The late Pleistocene, roughly from 126,000 to 11,700 years ago, was not a static deep freeze, but rather a dynamic ballet of climate extremes. When we speak of the Ice Age, it's crucial to understand that it wasn't a singular continuous event, but a period characterized by cyclical fluctuations between colder, glacial periods and warmer, interglacial periods. Our own Holocene epoch, which began 11,700 years ago, is merely the latest of these interglacials. The late Pleistocene was dominated by the last major glacial cycle. Imagine a world profoundly different from today. Vast sheets of ice, kilometers thick, ground slowly across continents, reshaping landscapes and locking away immense volumes of water. These were periods of immense cold and aridity. For context, picture the Earth's average temperature several degrees Celsius lower than it is today, a difference that might sound minor, but had catastrophic global ramifications. The most extreme phase of this glacial period was the last glacial maximum, or LGM, which peaked between approximately 20,500 and 19,000 years ago. During the LGM, the ice sheets reached their maximum extent. In North America, the colossal Laurentide ice sheet covered much of Canada and extended deep into the United States, reaching as far south as Illinois and New York. To its west, the Cordilleran ice sheet capped the Rocky Mountains. Across the Atlantic, the Fennoscandian ice sheet enveloped Scandinavia and parts of northern Europe. These immense frozen fortresses acted as massive climate engines, deflecting weather patterns, creating rain shadows, and amplifying global aridity. The impact of the LGM was truly transformative. With so much water locked up in land ice, global sea levels plummeted by an astonishing 120 to 130 meters. That's over 400 feet lower than present levels. This massive drop exposed vast continental shelves, creating entirely new land masses and land bridges that would prove pivotal for both animal and human migration. The climate across unglaciated regions was generally colder, windier, and significantly drier. Dust storms were far more common, depositing nutrient-rich loess soils across vast areas, sometimes hundreds of meters thick, which would later become fertile ground, but at the time contributed to harsh, abrasive environments. Vegetation zones shifted dramatically. Forests retreated, giving way to widespread grasslands, tundras, and even deserts in areas now temperate. The very air was different too, with higher concentrations of dust and altered atmospheric circulation patterns. Ocean currents, the planet's great heat regulators, were also profoundly altered by the ice sheets, further contributing to global cooling. As the LGM began to wane, roughly 19,000 years ago, the planet entered a period of general warming. This wasn't a smooth linear progression, but a stuttering, often dramatic climb towards warmer conditions. Deglaciation began, with the immense ice sheets slowly, then sometimes rapidly retreating. Meltwater torrents carved new rivers and lakes, and the rising global temperatures caused sea levels to climb steadily, eventually submerging the newly exposed land bridges. This warming trend was not without its own dramatic climatic shifts. One particularly famous and crucial event was the Younger Dryas, a sudden severe cold snap that occurred between about 12,900 and 11,700 years ago. After a period of significant warming, temperatures in the northern hemisphere abruptly plunged back to near glacial levels, likely due to a disruption of the North Atlantic Ocean circulation by freshwater influx from melting ice sheets. This brief, approximately 1,200-year-long return to glacial conditions was followed by an even more abrupt warming event, marking the definitive end of the Pleistocene and the beginning of the Holocene epoch, our current interglacial. This rapid oscillation in climate, from deep freeze to warming, then a sharp return to cold, followed by a final rapid warming, created an environment of enormous stress and constant change for the planet's inhabitants. One of the most profound geological consequences of the last glacial maximum's lowered sea levels was the emergence of the Bering Land Bridge, a vast unglaciated landmass that connected northeast Siberia with western Alaska. This wasn't a narrow strip of land, but rather a subcontinent, sometimes hundreds of kilometers wide, known as Beringia. For tens of thousands of years, this broad expanse formed a crucial ice-free corridor, acting as a global freeway for both flora and fauna. Beringia itself was a unique environment, a cold, dry, productive grassland steppe, quite distinct from the ice-covered regions surrounding it. Crucially, it remained largely ice-free because the air was simply too dry to support the formation of massive continental glaciers, despite the extreme cold. The significance of the Bering Land Bridge cannot be overstated. For animals, it was a biological superhighway. Species like woolly mammoths, bison, horses, camels, lions, and wolves moved freely between Asia and North America, facilitating genetic exchange and expanding their ranges. This two-way traffic enriched the biodiversity of both continents, creating vast interconnected faunal communities. For example, horses, which originated in North America, migrated to Asia across Beringia, only to return much later with European explorers. On the other hand, mammoths, bison, and eventually humans migrated from Asia into North America. This intercontinental exchange meant that the genetic health of many species was robust, allowing for adaptability and resilience across varied landscapes. It also, however, meant that diseases could potentially spread more easily across continents, a factor that might have played a subtle role in population dynamics. But perhaps most importantly, Beringia provided the crucial pathway for the peopling of the Americas. Anatomically modern humans, having originated in Africa and spread across Eurasia, eventually reached the northeastern tip of Asia. When sea levels dropped during the LGM, They, or their direct ancestors, were able to cross this newly exposed land bridge, becoming the first humans to set foot in North America. For thousands of years, these early inhabitants lived and thrived within Beringia itself, adapting to its unique environment before eventually migrating south and east into the vast, unexplored landscapes of the American continents. The eventual submergence of the Bering Land Bridge, as sea levels rose with the post-LGM warming, had equally profound effects. It isolated populations that had once been freely mixing, leading to genetic divergence and, in some cases, contributing to the extinction of species that could no longer migrate to find suitable habitats or mates. This periodic opening and closing of Beringia was a powerful driver of evolution and biogeography throughout the Pleistocene. The late Pleistocene world was a mosaic of interconnected ecosystems, each playing a vital role in supporting the rich tapestry of megafaunal life. The dominant and most iconic of these was arguably the Mammoth Steppe, sometimes referred to as the Mammoth Tundra or Steppe Tundra. This was not the barren, boggy tundra we often envision today, nor the semi-arid steppe of modern Central Asia. The Mammoth Steppe was a unique, highly productive biome that spanned vast stretches of northern Eurasia and Beringia, characterized by extreme cold, dryness, and strong winds. Despite the harsh conditions, it was a remarkably rich and diverse grassland ecosystem. Its productivity was key to sustaining the incredible biomass of megaherbivores like woolly mammoths, woolly rhinoceroses, steppe bison, and horses. What made the Mammoth Steppe so productive? Scientists still debate the precise mechanisms, but several factors are frequently cited.